In part 1, the first Pencast related to solving related rates problems, we illustrated a 4-step process. We will further illustrate this process with a related example. The length of a rectangle is decreasing at the rate of 5 centimeters per second, while the width is increasing at a rate of 3 centimeters per second. Find the rate of change of the perimeter of the rectangle when the length is 10 centimeters and the width is 8 centimeters. In the previous problem, we were finding the rate of change of the area of the rectangle. So we write each rate in the problem as a derivative. One of the rates, as before, is 5 centimeters per second, as in the previous problem. What is changing at the rate of 5 centimeters per second? It's the length. So the rate of change of length with respect to time is, and it's really negative 5 centimeters per second because the length is decreasing. Again, your units are key here. A measure of length is centimeters, a measure of time is seconds. Okay, we have the 3 centimeters per second. And that's the rate at which the width is increasing. So that's dw dt. The derivative of width with respect to time is a positive 3 centimeters per second because the width is increasing. And we want to find the rate of change of the perimeter with respect to time. So we want to find the derivative of perimeter with respect to time, dp dt. Okay? Second step, identify the dependent variables in the derivative. So again, as in the previous problem in part 1, our dependent variables are length, width, and perimeter, right? Although in the previous problem we had area, now we've got perimeter. But they are length, width, and perimeter. So I need an equation that relates these dependent variables. How are the length and width and perimeter related? Well, what is the shape here? It's a rectangle, isn't it? And we know that twice the length plus twice the width is the perimeter. So the perimeter is 2L plus 2W. Again, you always want to write an equation that relates the dependent variables from step 1. Sometimes, we all knew this equation. Sometimes, you might have the radius of a sphere, and you need to relate the radius of a sphere to the surface area. So you might have to Google a formula for that, okay? Step 3 is always differentiate both sides of the equation in step 2 with respect to the independent variable time. So we start out with perimeter is 2L plus 2W, and you want to take the derivative of both sides of that with respect to time. Okay? Derivative of sums, the sum of the derivatives. The derivative of 2 times L with respect to t, constant multiple rule. 2 times the derivative of L with respect to t. The derivative of 2W with respect to t, again, constant multiple rule. 2 times the derivative of W with respect to t. So the result from step 3 is we now have an equation that relates these derivatives from step 1. Again, the derivative in step 1 were dL dt, dW dt, dP dt, and we now have an equation that relates those 3 rates. Step 4, substitute values into this equation from step 3 and solve for the requested derivative. Well, we're trying to find what? dP dt. So dp dt equals 2 dl dt. So what's dl dt? It's negative 5 centimeters per second plus 2 times dw dt. dw dt was 3 centimeters per second. I'm just substituting the known values into this equation that resulted from step 3. So my answer, the rate of change of the perimeter with respect to time, is negative 10 plus 6, so that's negative 4 centimeters per second. Are the units appropriate? Well, yes, because perimeter would be a linear measure, so units such as centimeters are appropriate. Time, seconds, is appropriate. So what's happening here? The perimeter is decreasing, right? If the length of a rectangle decreases at a rate of 5 centimeters per second and the width increases at a rate of 3 centimeters per second, well, you can see that the quantity 2w plus 2l, right? You can see that that quantity is going to decrease over time, isn't it? Now, one reason I wanted to look at this particular example where we're finding the rate of change of perimeter with respect to time was that in part 1, we took the same problem and we found the rate of change of area with respect to time. And you'll notice something different. dp dt is 2 dl dt plus 2 dw dt. Did this depend on W and L? In other words, in this problem, did we ever use the fact that length is 10 centimeters and W is 8 centimeters? In this particular problem, that's just extraneous information, isn't it? The fact that the length is 10 centimeters and the width is 8 centimeters. We didn't need those values. The derivative of perimeter with respect to time is twice the derivative of the length with respect to time plus twice the derivative of the width with respect to time. The deal is the perimeter is changing at a constant rate. It's not dependent on the particular time. Now, in both these problems in part 1 and part 2, the length of the rectangle was decreasing at a constant rate, 5 centimeters per second. The width was increasing at a constant rate, 3 centimeters per second. But in the first problem, the rate of change of area with respect to time, if you go back and look at that, it was what? It was the length times the derivative of the width with respect to time, plus the width times the derivative of the length with respect to time. In other words, when we had L times W here for the area, we had to use product rule. And note that in that formula, we ended up with an L and with a W. So we had to use this 10 centimeters and 8 centimeters. Again, dp dt is 2 dl dt plus 2w dt. dl dt is constant, dw dt is constant. The derivative of perimeter with respect to time doesn't depend on a particular instant in time. In other words, it's constant.